When we're doing complex numbers, sometimes we need polynomials. So because we haven't done the polynomials topic yet, this is just a little run through on what we might need. So if a polynomial, which we'll define as px, is divided by x minus a, then the remainder is the value of the polynomial when x equals a. So if we've got our polynomial, we'll denote it by px. If it is x squared plus x plus 3, if we want to divide that polynomial by x minus 1, then by plugging in 1 for x, we get 1 squared plus 1 plus 3, which equals 5. So the remainder when you divide x squared plus x plus 3 by x minus 1 is 5. That's called the remainder theorem. We'll have a look at how to do that another way, but that's just a little bit of an introduction. Now, if x minus a is a factor of the polynomial, then really what should happen is that the value of the polynomial when x equals a equals 0, because it's a factor. To show if it is a factor, then what makes that 0? It's 1. So we plug in 1 into the polynomial and hopefully it will equal 0. So replacing all the x's now with 1's, get 1 to the 4th minus 2 lots of 1 cubed plus 2 lots of 1 minus 1, and we do in fact get 0. This is called the factor theorem. Once again, we'll have another look at that when we do division of polynomials in just a moment. So, division of polynomials. Just like long division from primary school, we can divide two polynomials. So, from the example that we had before, we can divide the polynomial x squared plus x plus 3 by x minus 1. So we have to say to ourselves, what do we have to times x by to get x squared? And the answer to that is x. So I'll pop that up the top there. And then I multiply x by both those things out the front. So x times x is x squared, and x times minus 1 is minus x. And then I need to subtract those two lines. X squared minus x squared is 0, plus x minus minus x will be x plus x, which is 2x. And I bring down the plus 3. And then I do the same thing again, but this time for 2x plus 3. So I say to myself, what do I have to multiply x by to get 2x? And the answer is a plus 2, so I put that up the top. Then I multiply that plus 2 with both terms out the front of the division. So I end up with 2x minus 2. And then I need to take away those. 2x minus 2x is nothing, plus 3, take away negative 2 is 5. So the remainder here is 5. So that means x squared plus x plus 3 will equal to x minus 1 multiplied by what we had up the top there, x plus 2 plus a remainder of 5. And that is the same remainder as we looked at before when we looked at the remainder theorem. Looking at the other example that we had for the factor theorem, if I want to divide x to the 4th minus 2x cubed plus 2x minus 1 by x minus 1. You notice I've left a gap there, and that's because there are no x squareds. And I need to be mindful that the powers of x go down by 1 each time. So I say to myself, what do I have to multiply x by to get x to the 4th? And the answer to that is x cubed. Then I multiply x cubed by both the terms out the front. X cubed by x is x to the 4th, times it by minus 1, and I get minus x cubed. Then I have to subtract. X to the 4th minus x to the 4th is 0, so I don't have to write anything. Minus 2x cubed, take away minus x cubed, is the same as minus x cubed. And then I have to bring these other terms down. So I've got plus 0x squareds plus 2x minus 1. Then what do I have to multiply x by to get minus x cubed? I have to times it by. minus x squared, and then timesing x squared by the two terms out the front. X squared times x will be x cubed, negative, then minus x squared times minus 1 is plus x squared. If I subtract those, minus x cubed take away negative x cubed is nothing. 0x squared take away x squared is minus x squared. And then I have to bring down the other two terms. Then what do I have to multiply x by to get minus x squared? The answer to that is minus x. So if I times both those terms by minus x, I get minus x squared plus x. I subtract those and I end up with x minus 1. And then what do I have to times x minus 1 by to get x minus 1? And the answer to that is plus 1. So I put that down there. And when I take those away, I'm left with nothing. So that is the factor theorem. Okay, if I have a term that I'm dividing by, or an expression that I'm dividing by, and my remainder is 0, then it is a factor. So what I can do from here is, I know from what I've just done before that that polynomial is the product of x minus 1 and what was on top. So x cubed minus x squared minus x plus 1. Then I can use whatever method I know how, but I'm going to look at these first two terms. They've got a common factor of x squared, so I'm going to take that out the front and I'm left with x minus 1. Then here, if I take the negative outside, negative 1, I've got my x minus 1 left inside the brackets. Then my x minus 1 is there. This time, x minus 1 is the common factor, and I'm left with x squared minus 1. That's a difference of two squares. So x minus 1, x plus 1. And so then, being completely factorised, it's x minus 1 all cubed times x plus 1. The other thing we might need to remember from polynomials, if you've got ax squared plus bx plus c equals 0, and the roots are alpha and beta, we remember that the sum of the roots is minus b on a, and the product of the roots is c on a. Now we can go a bit further than that to have a look at cubics. So if we've got a cubic, ax cubed plus bx squared plus cx plus d. This time we're going to have three roots, alpha, beta and gamma. If I add the roots up one at a time, like I did in the first one, I still get minus b on a. We'll look at why when we do polynomials later. If I want to add them up two at a time, so there's three different combinations there. This is the sum of the roots two at a time. It's once again c on a, the same as before. And then if I want to do the product of the roots three at a time, but in the first one there wasn't three roots, so we couldn't have an answer to this. But this time the product of the roots, product of all the roots, we went from minus b on a in this one, plus c on a, and now we go to minus d on a. And those bits of information will be useful when we're doing a little bit more work on complex numbers that involve polynomials.